because we have to. So we're going to be talking about alkenes, alkynes, and aromatic compounds today. And these are functional groups that we introduced yesterday. So I wanted to put this picture down here. This is actually in your textbook as well. These are some pictures of some antibiotics. They're called indiene antibiotics. And it's a new class of antibiotics that they're checking out for their anti-tumor activity. But if you look at these molecules, you can see all the aromatics in these, right? Aromatics, remember, are a ring structure with alternating single double bonds. And so they're really significant biologically and physiologically. You'll see them in a ton of different biological compounds. And this was just an example that I thought was really cool. It's kind of some new stuff. You see these triple bonds in here. So this ring structure right here with the triple bond, that's actually where they get their name from. Same thing over here. It's kind of the bold ring with the triple bond. So anyways, we're going to jump into, this slide right here. So we talked about this. I mentioned it yesterday when we were on the lab, but I really want to define it today. Alkanes are what we spent our time on yesterday. And alkanes, these are saturated. Okay. Because all the carbons have 4 bonds and they're all filled in. But alkenes and alkynes are considered unsaturated because they have a double or triple bond. So the carbons will end up with 4 bonds, but they're not considered saturated because they're not all single bonds. Okay. So we call alkenes and alkynes unsaturated compounds. And that's where this whole, I tried to write this in yesterday, but see, when you have a formula, the way the carbon hydrogen ratio works out is like this. So CN and then H, and down here it'll be 2N plus 2. I know it's kind of small. I don't know if you can see it very well. But if the number of hydrogens relates to the number of carbons from this mathematical formula, so say you have 5 carbons, and you plug in 5 for N in this spot right here, 2 times 5 plus 2, you should have 12 carbons. That's when you know it's a saturated compound. Okay, if you calculate that, take the number of carbons, plug this into this little formula and calculate the number of hydrogens. Okay, but if for some reason you have a compound such as, say, C2, H4, okay, you actually had this yesterday on the lab, we would consider this unsaturated because when you calculate, if you take this 2 from the carbons and calculate how many hydrogens you would have on a saturated compound, you're not going to get 4. You would get more than 4, okay? So just know the relationship between saturated and unsaturated. I may ask you on exam, here's a list of molecules, which one's saturated, which are unsaturated, something like that. Okay, alkenes. These are hydrocarbons containing a what? What do you think should go in the blank? A carbon-carbon double bond, right? And cycloalkane, or alkenes, sorry, these are hydrocarbons with a double bond in a ring system. And we're going to look at a lot of examples for that and how to name those as well. We learned how to name cycloalkanes yesterday. So we're going to talk about more rules for naming today, and a lot of them, different pieces that we used yesterday will apply to today, but there's going to be a few new rules we introduce for how to name alkenes, cycloalkenes. And then even alkynes have a carbon-carbon what? What do alkynes have? Do y'all remember from yesterday? Anybody? Should pull the chat up. Do y'all remember what alkynes have? A carbon-carbon what? What kind of bond?
Is it a triple bond?
It is a triple bond, okay? Oh. Oops, sorry, I have the word bond. Okay. So those are some of just our definitions. Definitely be working on memorizing those functional groups. Okay, you're going to need to have those memorized for exam 1. So don't wait till this weekend to memorize those. This picture over here, I want to talk about this. So ethylene, and you drew this in lab yesterday, C2H4. This is ethylene. Okay, we know it's F is the root word because it's a 2-carbon compound. And it's got this double bond, so you have the name ending ENE. This is the top produced organic compound worldwide over all other organic compounds. I thought that was fascinating. Guess how much of it we make worldwide every single year? Anybody even have a guess? I could not believe this. 20 million tons. We make, I can't even fathom how much that is. 20 million tons. This is a plant. I don't know if you can see in the picture, it's kind of faded. But behind this, the picture is molecule. This is a plant that just makes, it's just to make ethylene. Okay, it's massive. You can see all the different buildings and it looks super complicated. But ethylene gas, the way it relates to us is a lot through our foods. Okay, so this is the gas that is actually responsible for ripening all kinds of foods. Okay, has anybody ever been told, like, if you want to ripen something really fast, put it in like a brown paper bag and like fold the bag up? That's because what you're doing is you're in a closed container, you're increasing the concentration of ethylene gas. So when as it's produced by the fruit, it can usually just dissipate into the air. But if you put it in a sealed container, it just stays right there and the concentration of it increases. It helps ripen the fruit or the food faster. Okay, so, all right. Naming. Okay, so some more rules here. How do we name the parent compound? So we're going to identify the longest continuous chain of carbons, and we're going to name it according to the number of carbons in the chain, just like for an alkane, but here's the kicker. It must include the double bond. Okay? So for example, I put this example here for a reason. Look at this molecule right here. How would we number this? You would be tempted to number it starting with this carbon and saying, okay, that's carbon 1, 2, 3, 4. And then if I go down 5, 6, 7, that's my longest chain. But I can't number it this way when I have an alkene, when I have a double bond, because if I were to number it with just this top part and then just this bottom sequence with this carbon right there included, but not these two over here. So I'm just numbering 1, 2, 3, 4, 5, 6, 7. That does not include the double bond. I have to number the chain so that the double bond's included. So the way I have to number it is like this. Wonder if I can doodle. I want to just draw. I don't think it will let me. I want this to be carbon number 1. Wait. You might be tempted to number this carbon number 1. The second rule, though, when you go ahead and read the second rule, number the carbons in the main chain so that those with the multiple bonds have the lowest index number possible. So that's going to tell us what end to start numbering from. So instead of naming this carbon number 1, I have to name, man, it's going to be interesting today. I have to name this as carbon number 1, okay? Make that red. Okay, that's carbon 1. Then this one's going to be carbon number 2, carbon number 3. I write this down on your paper as I'm going. I'm very limited in my ability to annotate my slides today. And then this would be carbon number 4, 5, and then this last one would be carbon number 6, okay? So I'm going to drag this over here. This is going to be carbon number 6. All right. So that's the way we would number it. And then what we see is that this double bond, these carbons in the double bond, these are going to get the lowest index numbers possible. So now what are the carbons? How would I number these? This would be carbon 2 and 3. All right. So this would be carbon 2. I can just hit paste, should be. And that one's going to go right here. We'll make him carbon number 2, okay? And then the next one's carbon number 3. So that's what rules number 1 and 2 tell you. How to number the chain so that the double bond's in there and they get the lowest numbers possible. All right, and then also, so what we're saying, begin numbering at the end near the double bond. All right, we got that. But if the double bond is equal distance from both ends, well, then what do? It doesn't matter which way I number, right? Well, you still have to take into account if you have any substituents branching off. Because if you do, you want to start near the end with the first branch point. Okay, somebody sent a message. You might be able to draw if you hit the draw tab. There should be an option to doodle. Okay, help me. Somebody help me with this.
It should be at the top ribbon where it says like next to insert and design. If you draw, there should be like a pin.
Awesome. So I can say like, I can just like circle things. Well, that was good. Undo. If I want to draw in red. Okay, well, okay, there we go. Claire, you just helped me out big time. Thank you. Okay. There we go. All right. If the double bond is equal distance from both ends, then we're going to start at the end near the first branch point. So that's why I put this example right here. So look, the double bond is equal distance. No matter which way you start numbering, my carbons are going to be 3 and 4. Okay. But this second rule is telling us we have to, because we have this methyl group branched right here, we have to start numbering here. So we're going to say that's carbon number 1. This is carbon number 2. This is going to be carbon number 3. Okay. Oh, I'm sorry. That's not right. We're going to continue numbering. This is carbon number 3. Okay. And then when we name this, so let's actually try to name this really quick. You're going to use the rules like we did from yesterday. Okay. We're going to, whoops. We'll have a methyl group branched off carbon 2, right? So when we name this, we're going to say 2-methyl. This is where I could type, but I don't want to go back and forth. 2. See now, but I want to type.
Do we need a dash between the 2 and the methyl?
Yeah, I'm trying to type it instead.
Okay.
No, you're good. I'm still on draw. So if I go back to draw, now if I want to switch back and forth between draw and type really quick, how can I do that? I don't want to draw anymore. I just want to type.
Press on the draw button again. It should take you off.
Okay. So it will be 2-methyl. And then how many carbons do we have in the chain total? We actually didn't finish numbering it. 1, 2, 3, 4, 5, 6. Okay. So it's we would be tempted to say hexane, but this is an ene, right? So it's got to be hexene. So 2-methyl, and we have to include a number that tells us where the double bond occurs. All right. And I think that is going to be on the next rule. So we didn't get to that rule just yet. But the way it works out is you'll say 2-methyl, and then I'm going to put a 3 because that's telling me the first carbon of the double bond. 3-hexene. Okay, so this 3 right here, I'm going to highlight that. This 3 is telling me which carbon in this chain is the first carbon of my double bond. Okay, so I've got to include the 3. This is kind of a different aspect than we saw with alkanes. This is a little bit of a new rule. Include a number that tells you the first carbon involved in your double bond. All right.
Does it need a dash also?
Do what?
Does it need a dash also between 3 and hexane?
Yeah, one more dash. No, you're perfectly right. So 2-methyl, 3-hexene. Okay. If you have a triple bond, then the name ending becomes YNE, right? So if we're going to do this one, which end should we start numbering on? Do y'all think we should start numbering over here on the left or down here on the right? This one's closer to the first branch point, but this one is closer to the double bond. So which way should we or sorry, the triple bond. Yes, we're going to start numbering right here, the one closer to the triple bond. So we're going to call that carbon 1, call that carbon 2, this carbon 3, keep going, 4, 5, 6, 7, and then actually doesn't matter which way you go. We could call this 8 or this 8, but for the sake of clarity, it looks better to continue in the straight chain. Okay, and we see that we have a methyl group branched off carbon 7. Okay, so if we're going to name this, we would call it 7-methyl 2 oct, OCTYNE, okay? Because it's got 8 carbons, so the root word is oct for 8, and then YNE indicates that it is a alkyne because of the triple bond, okay? So 2-methyl or 7-methyl 2-octine. So cycloalkenes, this is a ring structure that has a double bond in it. It could have one double bond, it could have more than one double bond. If it's got alternating doubles and single bonds, then you know it's an aromatic. But if it just has 1 or 2 double bonds, that is an alkene. And sorry, I have some of the chat and things are like in the way of part of my text. But we're gonna give when we number this. So remember, part of naming is getting the numbering right. When we number this, we're gonna number carbons 1 and 2 so as to give. These are going to be in the double bond. Carbon atoms are assigned index numbers of 1 and 2. There we go. Okay, so we're going to number this is carbon 1, and this is carbon 2. All right, and then we're going to continue putting the numbers in so that this, if there is a substituent, it gets the lowest number possible. So we're going to make this carbon 3 and this carbon 4. If we number the other way around, then this substituent ends up being carbon branched off carbon 5. Okay, and branching it from carbon, numbering it as carbon 4 is lower than number 5. Okay, so that's why we're numbering in a clockwise direction here. Don't get stuck in your head that you always number the carbons in a clockwise direction. That's not true. It depends, okay? Where your substituents are should tell you which way you need to number it, clockwise or counterclockwise. Does that make sense? Okay. So now I think we can go to the next slide. Anybody still drawing on this one, on the previous slide?
I was.
Okay, let me go back real quick. Guys, this is, you can probably tell I'm like out of my zone right now.
I got it.
Okay. So now we're going to write the name as a single word. Okay. So it says indicate the position of the multiple bond in the chain by giving the number of the first multiple bonded carbon. So I've actually already addressed that. We did that on the previous slide. If more than one double bond is present, use prefixes such as di, tri, tetra, and so forth. Okay. We actually don't have an example yet where there's more than one double bond. But we did yesterday examples where we have more than one identical substituent. So if you had 2 methyl groups branched off, you use words like dimethyl. Okay, but same thing here. If we have more than one double bond or more than one triple bond, you just use words like di in front of your parent name. Okay. So the same rules apply from alkanes, commas, and hyphens, and then assigning numbers to the branching substituents. So let's do a practice. This is a good one to practice on. So we've got 2 substituents, and we see that this is going to be some kind of alkene because we have a double bond. So it looks a little bit tricky here. How do we need to start numbering this? Like, which carbon in this structure do you think I should number as carbon 1? You have to remember, identify, okay, what is my longest carbon chain? Even if I have to turn corners, even if it looks like something that is branched off is actually part of the longest chain.
We'd start from the left and then go up on the ethyl group.
Start from the left right here.
Yes.
So number this carbon 1, 2, 3, 4, 5.
No, 5 on the second end of the double bond.
5 right here.
Yeah, then go up.
And then
6,
7. Okay, but remember we have to number it so that where is it? You want to begin numbering at the end near the multiple bond. So Madison, you have the right chain. We just need to start numbering from the opposite direction.
Okay.
Does that make sense? So we're going to call this carbon number 1, because when we do that, if this is carbon 2, this becomes carbon 3. Okay, and then this is carbon 4. So now I have in these red numbers I'm writing in, that's when it says index number, that's what it means. Those are the index numbers. Now our double bond has index numbers of carbons 3 and 4 instead of 1, 2, 3, 4, and 5. Does that make sense? So this will be carbon 5, 6, and 7. Okay. So now this is going to be, what's my root parent name for this compound? So remember, we got meth, eth, prop, bute, pent, hex. 7 is
Hept.
hept. Okay, so this is going to be a heptene. That's my root parent name. And I just have one double bond, and the first carbon in my double bond is a 3. So it's going to be 3-heptene. But I have to now account for any substituents and put those in as prefix before this word. So what substituents do I have?
You have an ethyl group on 3 and then a methyl group on 4.
Look close. So this right here, this is the substituent. That's not an ethyl group.
Methyl. Or no, that's not methyl.
And what else? What is this one?
Methyl.
Okay, so we have two methyl groups. One branched off carbon 3, and another one branched off carbon 4. So the way we're going to write this is we'll say 3,4-dimethyl 3-heptene. Okay, 3,4-dimethyl, because we have two methyl groups, 3-heptene. Okay, questions on what we just did? Now I want you to draw the structure, if there's no questions. I want you to attempt to draw the structure of 3-ethyl, 4-methyl, 2-pentene. Draw it in the condensed form and as a line structure. So I'm going to start, the way I read this, I always go to the end and I read what's my parent compound, like what is the root chain here? It is a pentene and there is a double bond. What does this 2 mean? This 2 right here means the double bond starts, it's between carbon 2 and 3. Does that make sense? So I'm going to draw a carbon bonded to a carbon, and then I've got a double bond here. I'll go back and write the condensed structure, but I need to see it first. That's how my brain works. Okay, so I'm going to draw out the Lewis structure. So there's my double bond, and then I got 3 carbons. I need 2 more, right? Because pent means 5. This is a 5-carbon chain. So I've got 3, then here's carbon 4, and then here's carbon 5. Okay. Now, we've got some substituents. Off of carbon 3, I've got an ethyl group. So this is carbon 3 right here. It doesn't matter if you branch it up or down. And an ethyl group is a 2-carbon substituent. So that's going to be CH2, CH3. I feel like I am slow as Christmas with this draw tool. Then we have a methyl group branched off carbon 4. That's what this portion means. So now we're going to draw that. So here's carbon 4. Doesn't matter if you go up or down. I'm going to go up so I have a little more space. Methyl is a 1-carbon substituent. There we go. Now the rest should be hydrogens, right? So I should have 3 hydrogens, boom, 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 branched off that. I'm not going to write all these in for time's sake. 2 carbons, nope, just 1 carbon. Count carefully because I got a double bond here. So just 1 hydrogen. I keep saying carbon. 1 hydrogen branched off that carbon. So 3 hydrogens off carbon 1, 1 hydrogen here. Look at carbon 3 here. How many hydrogens should I have bonded to carbon 3?
None.
None. It's already got 4 bonds. 2 in the double bond, a bond downwards for the ethyl group, and then another bond in the next carbon. So no hydrogens branched off that one. This carbon 4, should get 1 hydrogen because to complete the octet needs 4 bonds. So put a hydrogen there. And then 3 hydrogens branched off this last carbon. 1, 2, 3. So now I can write the condensed structure. Okay. So how am I going to denote in a condensed structure that these groups, the ethyl and the methyl groups, are branched?
Would you put them in parentheses?
That's what I'm going to do. Yesterday I said you can actually draw them branched up or down, or you can put them in parentheses within the same thing. So the way I'm going to type it, whoops, I'm going to type it. So you got CH3, that's this first group. Then you got CH, that's my second carbon. And then you've got C. Okay, so this is carbon 3, corresponds to this 3rd carbon right here. And then I'm going to put a parentheses because I want to indicate off of carbon 3, I've got an ethyl group. And I'm going to type my ethyl group in that parentheses. So now I have my ethyl group in parentheses. What that means is branched off the preceding carbon. Then I've got carbon 4, CH, and branched off of carbon 4 is a methyl group. So I'm going to type CH3 in parentheses. And then I have carbon 5 right here. So that's CH3. Okay. So again,
I have a question.
yes.
On the, okay, after at the start, when you put CH3 and you put your second CH, would it not be CH2? Because in there supposed to be, oh, just kidding. There's the double bond. Just kidding.
I almost drew in 2 hydrogens and then I did the same
I see
thing.
it now.
Okay. I'm going to zoom back out. Okay. So again, that's the condensed structure. So this is the condensed.
Do you not have to indicate that it's a double bond, or would you just know from knowing there's only one hydrogen attached to it?
It's implied by the number of hydrogens. That's why for me, I have to draw these things out first, or I would totally botch writing the condensed structure if I can't see it. Okay, now it asks us to draw as a line structure as well. Let me go back to the pen. Okay, so if I'm gonna draw this as a line structure, I know a CH3 group, okay, that's this first one over here, is gonna look like this. So I got a CH3, and then I have it, I'm gonna draw down to my CH, will be there, and then it's gonna go, remember we draw it kind of as zigzag lines. There's my double bond, so here's carbon 3 right here would be at this joint. And then off of carbon 3 is where I have my ethyl group. So I'm gonna draw up. Oops, I didn't mean to do that. I'm going to draw up. That's the CH2, and then a dead end to a CH3. And then I'm going to connect carbon 3 to carbon 4. And off of carbon 4, I have a methyl group. So I'm going to branch one down. And then I'm going to branch it over to carbon 5. So again, this is carbon 1. This is carbon 1. This is carbon 2. This is carbon 2. We've already labeled carbon 3 over there. This is carbon 3. This is my ethyl group. Okay. Then this is carbon 4. And this is carbon 5. And this is the methyl group. I'm just going to put an M for methyl. Okay. So can y'all see it, how it corresponds to the real structure, the line structure? So I definitely, on the exam next Monday, I expect you to be able to do a problem like this. I think this is a great problem. I give you the name, you draw it out, and then you either write the condensed structure or the line structure. You definitely should feel comfortable with both, okay? Any questions on what we just did? This is not necessarily easy. There's a lot of layers here, a lot of rules to know. Okay. We'll keep moving. All right, we're going to talk about isomers a little bit more. Today's lab is all about isomers. We aren't exactly going to be doing cis-trans isomers. You're going to be doing isomers from a lot of stuff from like yesterday's content. But when you have alkenes, okay, a double bond, there's no rotation around double bonds the way there is around carbon-carbon single bonds. So this allows a new kind of isomer, and we call them cis-trans isomers, okay? And it's just possible for the alkenes, okay? We cannot have cis-trans isomers for alkynes, all right? And not for alkanes either, just for alkenes. What's gonna help here is if you can zoom in on your molecule on just the double bond, okay? And then from there, you're gonna imagine that you have ends and sides to your molecule, ends and sides, okay? And you're going to give anything that's branched off of these carbons, see how they kind of have grouped them A, B, and then D, E. You're going to kind of think of them as individual groups, okay? So this will make sense in just a second. We're going to explain cis-trans isomers with this molecule right here, C4H8. It's a bute molecule, okay, but butene. It's got one double bond, okay, butene. And the double bond can occur different places. So we can have one butene or two butene, all right? And we're going to look at the different examples on how cis-trans isomerization is possible with one butene or one or two butene. So here is, I'm going to zoom in just a little bit. Here is the image for 1-butene. Y'all can see that? You got it on your slide? It's 1-butene because the double bond occurs between carbon 1 and 2. Okay, so that's carbon 1 and that's carbon 2. So 1-butene. Now, off of carbon 1, we have 2 hydrogens. And then the rest of the structure is technically, if you zoom in on this double bond, the way I encourage you to up here with the structure, it looks like carbon 2 has this thing branched off of it, an ethyl group. It's not an ethyl group, it's part of the main chain. But that's what it looks like here. And then we have a hydrogen branched off carbon 2. Okay, what I want you to notice is the groups branched off, these carbons that are part of the double bond. All right, this one has 2 hydrogens, this one has a carbon group and a hydrogen. All right. What's different though, when you look at 2-butene, so here's a structure for 2-butene. The double bond is occurring between carbon 2 and 3. All right, so we got 1-butene and we got 2-butene. And this is how it would look if we zoom in on this double bond and then we're branching all the other substituents off of those carbons. It would look like you've got a methyl group. This is actually carbon 1 in the structure. There's carbon 1. Then we got carbon 2. This is carbon 3. And this is carbon 4. So this is butene. But if we look at it this way, what do you notice? Okay, how is 2-butene different than 1-butene? Okay, on 2-butene, we've got carbon groups off of carbon 2 and 3, off of both of the double bonded carbons. And then each of them also have 1 hydrogen. But on 1-butene, you've got 2 hydrogens on this side, and then you've got a single carbon group. So what am I trying to say? What's the point I'm trying to make? Well, when you have carbons like this, let's look at 2-butene. When you have carbons like this in the double bond, where they have different groups branched off of them, it's possible to get a cis isomer and a trans isomer. So this is actually, if you read the name carefully, if I zoom in a little bit more, they're calling this cis 2-butene. Why? Because these carbon groups that are branched off, let me see if I can circle them in a different color. Blue. These carbon groups right here and right here, they're on the same side. You see how they're both pointing up? Okay, so if your carbon, these are not real substituents, but they're like pseudo substituents. If they're both pointing towards the same side, we call that cis. Now we know that we can rotate carbon single bonds. We can't rotate the double bond, but it is possible to have another kind of isomer. So this is a totally different connectivity between the atoms. And if I can scroll down a little bit, that is where you get trans 2-butene. Where's my marker? Right here. Trans 2-butene. So how is trans and cis different? Look at it closely. Well, in trans, the carbon substituents, I'll circle them in blue too. These are pointing opposite directions. One's going up and one's going down. It may help you if you look at these ball and stick models over here. Okay, here's the double bond in the middle, and the carbon substituents on a cis isomer are pointing both the same direction, either both up or both down. But on a trans isomer, they're pointing opposite directions. One's pointing up, one's pointing down. Okay, now I'm going to go back over here to 1-butene, and then even 2-methylpropene is another isomer of our butene molecule. Why can we not have cis trans? I'm trying to find my pen. Okay, why can we not have cis trans isomers with these? Okay, well, I want to read this right here. If a carbon in the double bond has 2 identical groups, and when I say groups, it could just be a hydrogen, we consider that a group, then no isomers are possible. So that is why for 1-butene here, this carbon right here, we're saying that this hydrogen, these are 2 identical groups. This carbon has 2 identical things bonded to it. So no matter how you flip the other side, it's the same. You can't get a cis trans isomer with that. Okay, you have to have 2 carbon groups branched off of your carbon-carbon double bonds. Does that make sense? Yes, no?
I'm sorry, I got a little lost. Is that only when it's like hydrogens or?
Well, it could be identical groups. So look down at 2-methylpropene. That's a great question, Claire.
Oh, okay. Sorry, I didn't even see that.
It's a great, well, yeah. It could be hydrogens, or if it has just 2 identical groups. So it could be methyl groups. You could have, if it had 2 ethyl groups branched off the carbon, As long as the groups are identical, you cannot have cis-trans isomers.
Okay.
Okay.
Okay, I get it now. That makes sense.
Okay. We're going to walk through a little problem with this. I think it'll make more sense. So, let me zoom out on this slide. Okay, now y'all should be able to see. Whoops, that's yesterday's lecture. That's not what I want. Okay, now I should be able to see the whole slide. Okay, I'm going to go to the next slide. We got a practice problem. You may not feel like this clicks yet, but hopefully practicing it will. Okay. Draw a structure for both the cis-trans isomer of 2-hexene. Okay, so 2-hexene is going to look like this. Hex is how many carbons am I going to have in my chain?
6.
6.
All right, so let's draw that out. 1, 2, 3, 4, 5, 6. Okay, now where should I put the double bond?
Shouldn't you put it, I mean, would it be closest to the, like the second carbon? Like you can do either
Start
side?
with carbon 2 and 3. Yeah.
Okay, yeah.
This 2 means that carbon number 2 is the first carbon in the double bond. So I could not put it here, Robin, because then it would be called 1-hexene.
Yeah, okay, but does it matter which side? Like it makes more sense to obviously go like this because you read left or right, but would it matter if you went from that side and put
Well,
it
if I started numbering from this side, then my double bond would be here.
Yeah, would it matter though?
Doesn't matter.
Okay.
Okay, but we started numbering on the left, so if we're doing that, then this is carbon 2, so the double bond goes there. All right, now the rest are hydrogens, okay? So we got 3 hydrogens on this carbon. Okay, and on our carbon number 2, we have 1 hydrogen, completes the 4 bonds for that carbon. Carbon number 3, also 1 hydrogen. It does not matter if you branch it up or down. And then we got 2 hydrogens off of all these others. Okay, so this is our full structure for 2-hexene. Now it's what it's asking us to do is draw cis-trans isomers. So I'm going to redraw the structure, kind of like what you saw on the previous slide. All right, boom, this is a hydrogen, that's a hydrogen. Okay, this takes me forever doing it this way. Okay, there's our structure. So I'm going to redraw it so that it looks kind of like the structure we saw on the previous page. So I'm going to draw the 2 carbons in the double bond. Boom, boom. Now, off of this carbon, I'm going to highlight it in red. Off of this carbon right here, carbon 2, I have this hydrogen, okay, branched off, and I have this methyl group branched off, right? So that's what I'm going to draw. I'm going to draw the hydrogen pointing up, and I'm going to draw the methyl group. I'm just going to write CH3. Sometimes they write it kind of backwards like this because I want you to know the bond is between the carbons. Okay, so this is the methyl group. This is the methyl group I have boxed in red, and this is the hydrogen that I have boxed in red. That's off carbon 2. Off of carbon 3 here, so this is carbon 3, and this is carbon 3. What do I have? I have a hydrogen off of carbon 3, and I have, what is this group? We're going to treat this as a whole group. What is that? Anybody know?
Is it prop?
Propyl group. Good job, Abby. It's a propyl group. So off of carbon 3, I'm going to have eraser. I'm going to erase this little, there we go. Hydrogen. And it doesn't matter if I do it up or down. but I'm going to draw the propyl group. So I'm going to just write it CH2, CH2, CH3. And that is a propyl group. Okay. Now, I have drawn one of the isomers. Did I draw the cis or the trans?
Trans.
Trans, because one of these carbon substituents is pointing down. Draw an arrow for down. And one is pointing up. They're on opposite sides of my double bond. See that? The hydrogens, I'm not going to say they don't matter, but they're not the ones that tell us if it's cis or trans. It's the carbon substitute, the carbon branch points that we care about. So this is trans. Okay, now we got to draw the cis. So same thing, but this time I'm going to move that over a little bit further. Draw it right here. Carbon-carbon double bond. To make it cis, what do I need to do different?
They need to both be pointing up to the same side.
Either both pointing up or both pointing down. So I'm just going to draw them both pointing up. So it's like I'm going to rotate this side. It's like I'm going to switch those groups. The CH3 is going to point up. Okay, and I'm going to leave this side the exact same. The propyl group is going to be the same. So CH2, CH2, CH3. Okay, and then I got hydrogen in here. So you see how this is cis? Because my red arrows both are pointing up. And again, you could have drawn them both, oops, both pointing down. Okay, so this is cis. Okay, so does that help clarify what I was trying to explain on the previous slide? All right, so I
Yes.
have a poll question. You might want to draw these out. Actually, gosh, we're running tight on time. I would really like for you to try this on your own and see if you can figure this out, okay? We need to move on to the next thing because we're just running tight on time since I'm a little bit slower today. But this is a great example if you want practice before the exam Monday to work on, okay? Which of these? Only one of them has cis-trans isomerization. Two of them do not, okay? I'm going to jump over that though. Okay, properties. So properties of alkanes. Based on what we already know, or properties of alkenes, sorry. Based on what we already know about alkanes, what do y'all think about alkenes and alkynes? Are they polar or non-polar? Remember, polar or non-polar all depends on electronegativity differences. We talked about that word electronegative yesterday. Okay, so I'm going to remind you that carbon-hydrogen bonds are always non-polar. Okay, and then carbon-carbon, when you have identical atoms in a bond, these are always non-polar. So if you have a molecule that's primarily composed of carbon-carbon bonds and carbon-hydrogen bonds, is it polar or non-polar?
Non-polar.
Correct. Okay, alkenes and alkynes are held together by which of the following do you think? Hydrogen bonding, dipole, or London dispersion? Remind you, hydrogen bonding, you have to have a positively polarized hydrogen. You have to have an oxygen with a lone pair, or a nitrogen, or a halogen with a lone pair, or sorry, a fluorine. Dipole, to have dipole interactions, you have to be a polar molecule. London dispersion forces are the types of intermolecular forces that predominantly hold together nonpolar molecules. So based on that, what type of intermolecular force holds alkenes and alkynes together?
The last one.
Yes. Okay. And these are the weakest. London dispersion are the weakest. Hydrogen bonding are the strongest types of intermolecular forces. It takes very little energy to break apart molecules that are held together by nonpolar intermolecular forces, London dispersion intermolecular. It takes a lot more energy or more heat to break apart molecules held together by hydrogen bonding or dipole interactions. All right, next thing, alkenes and alkynes are, what do y'all think, soluble or insoluble in polar solvents, such as water? Remember, like dissolves like. We already said they're nonpolar, so do you think they're going to dissolve in something that's polar?
Insoluble.
Correct, insoluble. So if they're insoluble in polar solvents such as water, then the opposite is true. They are soluble in nonpolar solvents. They are nonpolar, so they're going to easily dissolve in things that are like them that are also nonpolar. So oils, okay, or organic solvents, a lot of organic solvents such as hexene or benzene or things like that are nonpolar solvents. Okay, overall, the properties of alkenes and alkynes are pretty, what do y'all think, similar or different to alkanes?
Different.
What did we say yesterday? Alkanes are mostly carbons and hydrogens.
Similar.
So they're nonpolar as well. And if they're nonpolar, then they have all the same properties. They predominantly experience London dispersion forces. They're not soluble in water, but they are soluble in nonpolar solvents. So they're similar. To alkanes. Now, unlike alkanes, they are more reactive. They're a little more flammable because of the double bond. Things can be added to that molecule very quickly. They can react. Those are electrons that are ready to interact with other things. So you have to store them very carefully. You don't want to put them around just anything. Here's a summary of all the properties we went over. Okay, so it's just a summary slide. I'm going to skip over it. But that's literally from your textbook, just summarizing all the things we just talked about, even with cis-trans isomerization. Okay. All right, now we're going to get to types of organic reactions. So there are 4 main types of organic reactions, and we actually did this in one of my classes last spring when we were classifying types of reactions. I thought it was kind of funny, but people said it really helped them keep the different reactions straight. So you have addition reactions. This is a kind. Elimination, substitution, and rearrangements. And what we did is we equated it to relationships. Okay, so addition, we said, is like getting married or having kids. You're adding on to the family. Elimination is like getting divorced. Okay, something is leaving the molecule. One molecule is breaking apart into 2 molecules, something like that. Substitutions, I didn't have a good example for this, but I was like, substituting somebody and you're like, that's probably never going to end well. And I didn't know if y'all had a thought for rearrangements. Somebody used to say like wife swap. There used to be a TV show like that. But anyways, these are a little more confusing, okay, and complicated when it gets to relationships. But these are the 4 kinds: additions, eliminations, substitutions, rearrangements. So we're going to kind of briefly look at different examples of these. Addition reactions. The base plain Jane example I could give you. Molecule A and B come together and make molecule C. Okay, so we said it's like getting married. 2 people come together and make one family. All right, so this is a general reaction in which a substance is added to the multiple bond of an unsaturated reactant. Okay, and it yields a saturated product. Okay, so you start with an alkene or an alkyne, and then you add some sort of molecule to it, and it adds on directly at the double bond. So X and Y, it doesn't matter for now. There is going to be a time where it will matter which carbon X goes to and which one Y goes to. And we'll get a little more specific later on. But you just see they're added across this double bond. One atom goes to one carbon, the other atom goes to the other, and the double bond, the electrons there is what's being used to help make those bonds. Okay, so the multiple bond disappears. You end up with a saturated, this would be a saturated product right here. Same thing, you can imagine it for an alkyne. It's just going to require double the amount of reactant, okay? Because you gotta you got to take away 2 extra bonds, all right, to make it a saturated product. Okay, elimination reactions are basically the opposite. You have one compound breaking apart into 2 things. Okay, so in a general reaction type, this is when a saturated reactant yields an unsaturated product. Here it's like you're making a compound with a double bond. So say you have this with the X and the Y added, well, these 2 leave and make their own product, and then 1 electron from each of these remakes the double bond. Okay, 1 electron from each of these bonds remakes the double bond. And then 1 electron, remember each of these have 2 electrons in them. So 1 electron is going with X to make the bond between X and Y, and 1 electron here is going with Y, and then 1 electron is folding down in between the carbons to make the double bond. Okay, so the single bond becomes a double bond, or a double bond can become a triple bond. So for a real example here, if you have, can I zoom in? If you have ethanol down here, and you have H and OH, what can H and OH make? They can make water, okay? These 2 leave, and then you remake the double bond, you make ethylene, and then water's your other product, okay? We're gonna get to this, it's called a dehydration. Why? Because water's leaving. When water leaves us, what happens? If we don't have enough water, what happens? We're dehydrated. So they call these dehydration reactions. Okay, so that's addition and elimination. We're gonna really dig into addition in a little bit and look at different kinds of addition. But for now, just know the general reaction type, what's happening. All right, 2 more, substitution and rearrangement. In a substitution reaction, you've got something like A and B plus C, and we're just rearranging. We're swapping B and C. C is taking the place of B, okay? So a general reaction in which an atom or a group of atoms, it could be a group of atoms, is replaced by another atom or group of atoms. So like a methyl group could get replaced. It could be a group of atoms that's being replaced, not just a single hydrogen or a single, I don't know, halogen or something like that. Here, this single hydrogen is being replaced by a single chlorine. It's like they're swapping, okay? So you get chloromethane in the end and hydrochloric acid, all right? Everybody see what's happening there? The chlorine is substituted for the hydrogen in this reaction. Okay, but it could be like a whole methyl group is replaced, not just a single hydrogen. Rearrangement reactions. General reaction type in which a molecule undergoes bond reorganization and you get an isomer. So nothing leaves here. So that's why I didn't even put a reaction. You're just rearranging things within the molecule. So for example, if you have this substituent group, well, if Y breaks off, it could bond to this carbon, and the double bonds being used up there to make this new bond to Y, okay? And that's what you get right here. And then we're rearranging the bonds. Now we end up with this double bond to X, okay? So we didn't lose any electrons. Everything just got rearranged. I'm gonna erase all my stuff so you can actually see it. Oh, a good example, converting cis isomer to a trans isomer, okay? Bonds actually have to break for this to happen because you can't just rotate the double bond. You can't just flip it. It kind of seems like you can, but you actually have to break the hydrogen-carbon bond and the carbon-carbon bond and rearrange the methyl and the hydrogen groups, okay? All right. Questions on those so far? Let's see if any of it sunk in. Classify the following as addition, elimination, or substitution. Do I have a poll question for this? Let me see. Yeah, I think I do. No, it's for the next slide. We'll use it on the next slide. Okay, so here, what do y'all think about A? We got the double bond and we got hydrogen, and then, so it's we got 2 things on the reactant side and we got 1 compound on the product side. So real quick at a glance, what do you think?
Is it addition?
Yep, it's addition. Oops. Okay. What about B? We've got 1 thing breaking down into 2 things. We have a saturated reactant and we have an unsaturated product.
Elimination.
Got to be elimination. We lost water. Okay, so what we did is, what actually happened here is the OH from this last carbon, and then one of these hydrogens, okay, breaks off to give us water. So that's why it's elimination. Okay, what do y'all think about the last one?
Substitution.
Okay, why do you say that, Cameron? You're correct. What's being substituted?
The KOH and the potassium chlorine at the end.
So the chlorine here, yeah, you're kind of all around it, and the OH are swapping. The K stays put, the potassium stays put, but the OH bonds to this, so we get an alcohol product, and then the chlorine, you get potassium chloride. So the hydroxyl group and the chlorine switch. Okay, now I'm gonna let you guys look at these next two. This one, these are a little more difficult. I'm gonna tell you, I think looking at it from a line structure point of view, I don't know, sometimes it helps to see it, but I think these are a little challenging. So I have a poll question for this. I wanna know what you guys think. What kind of reaction are these? You gotta look closely. And on the second one, on B, the molecule's like flipped upside down on the product side. So it's actually really hard to determine what's happening in B. But look at it and tell if you can see, like, see if any double bonds go away, see if any double bonds appear on the product side that weren't there on the reactant side. Sometimes that's a clue to tell you what's happening. So we have fumaric acid, but it looks a little bit different, okay, to malic acid on the product side. What went away or what appeared? Anybody have any thoughts?
Is the poll supposed to be functional groups? Or
Yeah, I think the poll is wrong.
Oh, it's wrong. I just had it
Oh.
up on the right one. Okay.
I got very
there it is.
confused.
So sorry, guys. Wow, this has been a day. Okay, is that right? Okay, reaction one is best classified as addition, elimination. So I wasn't even looking at the poll. I was looking at the slide. Sorry. I'm going to point a few things out. Maybe this will help you if you're struggling on this. Okay, so I noticed here there's a double bond right here. But on the product side, that's not there. It's gone away. So which of the four types did we say you start with a unsaturated reactant and you make a saturated product? Although we still have these double bonds, yes, but this bond right here is now saturated. So we're just talking about this double bond. It's unsaturated, these carbons, and now over here they're saturated. And it seems, okay, we didn't have anything pointing down right here. But now on the product side, we have this OH group pointing down. So it's like we're adding OH, and then something probably was added to this carbon too. Okay, if that electron is going to be, that double bond is going to be eliminated. All right, so think about that for number one. Number two is really weird because they flip everything. So like this O right here is pointing down on the reactant side, but this is the same oxygen just pointing up on the product side. And it's the bonds angle down to the oxygen here and here, but they angle up to the oxygen here and here. So what's different from reactant to product side is this right here. We got this We got this OH group branched off this carbon right here. We do have a carbon right here, but it doesn't have an OH group branched off of it the way it does. So 2, we also, same token, you may have noticed, this is a single bond, all right? But over here, it's a double bond. Okay, so consider that as you pick. All right, I think 6 of 7 of you voted. Go ahead and just guess if you're not sure. Okay, I'm gonna end the poll. There we go. Share results. So we got quite a few different, we got all the answer choices selected here. Okay, so the most popular vote for number 1 is addition, and that's what's happening, okay? Water is being added. How do I know this? Well, remember on line structures, we don't show hydrogens, okay? But it must be that a hydrogen is being added here and this OH is being added here, because if it was like a chlorine or an oxygen or a nitrogen or something, we would write that in, okay? We show oxygens, we show atoms like phosphorus, we show electronegative atoms. But if something's being added, it's not shown, it must be hydrogen. So hydrogen's being added here and OH is being added here, and it's eliminating that double bond. So we're adding water. That's what makes it addition. This is an addition reaction. And that's what we said on addition, is that you have a unsaturated reactant, you're making a saturated product. Okay, what about number 2? The most popular vote is elimination, okay? 4 people said elimination. What it seems like is happening, we have this OH group and then somehow it's gone on this side, okay? And look at, I'm gonna try to zoom in. I'm gonna try to zoom in. I'm gonna draw right off of this carbon right here. We don't see it in the line structure, but there is a hydrogen, right? Because we only see 3 bonds on this carbon. So it means one of those bonds that we don't see has to be to a hydrogen. For this carbon to have 4 bonds, it's gotta have 1 hydrogen bond. Okay, so what is being eliminated is not just this hydroxyl group, but this hydrogen as well. And then the electrons, 1 electron from that bond is going here, and 1 electron from that bond is going here, and it's giving us this double bond that we see between these 2 carbons. And then we're also generating water. So what we have overall, if we were to just generalize this, okay, that's pretty technical and specific. We have 1 molecule here, we've got 2 products on this side, okay? We have a saturated bond right here, we're making it an unsaturated bond. So this is definitely elimination. Okay, anybody just like totally lost on this? It's hard to see, but that's why the more familiar you get with line structures, I'm not gonna say these things will ever necessarily be easy, but you'll be able to spot these things a little better.
I have a quick question. It was easier with the line structure.
It wasn't or was?
It was.
You liked it with the line structure? Some people do. What was your question, Abby?
So did you say unsaturated was one that has a double or triple bond to a carbon?
Yes, that's all the way back here, slide 1, okay? Alkenes and alkynes are unsaturated because they have a carbon double or triple bond.
Okay, thank you.
Yeah. Okay. Guess what? I told you more addition reactions, okay? More addition reactions. So we're really going to dig into addition reactions. We got a couple kinds we're going to talk about, 3 or 4, I think. When what is specifically being added is hydrogen, we have a specific name for that kind of reaction, okay? So these are all additions. It's just under the umbrella of addition, we have different kinds of addition. So hydrogenation is the first. If you're going into dietetics, you probably will hear, or at least you might be aware of hydrogenation. This is what they do to fats a lot of times. So when you have saturated fats are the good fats, okay? Unsaturated fats, did I get that backwards? Unsaturated fats, well, there are some good saturated and unsaturated. What's really bad though is trans fats, okay? So I have this picture of fried chicken right here. A lot of the times when we're hydrogenating fats and we're adding hydrogen across these double bonds, making these unsaturated components, what we can end up with is trans fatty acids, okay? And that's been associated with high risk of heart disease and things like that. So a lot of times if you go look at the nutrition label on your food, you want to see zero trans fat, okay? Zero trans, can you all see that? Zero trans fat. That's what you want to see. But that's the kind of fat that's used in a lot of fried food, unfortunately, okay? So that's hydrogenation, okay? It yields a saturated alkane product and the multiple bond disappears, okay? So this is saturated. I'm just gonna write, wow. Maybe I'll just type it. This is now saturated. Never mind, I'm not gonna type it. Just write in your notes, this is saturated. Okay, another kind of addition, halogenation. So in your head, when you hear the word halo, the root word there is halogen. This should give you, I mean, the root word should tell you what it is. Hydrogen, okay, we're adding hydrogen. Halogen, we're adding a halogen. So we have just X here, but X can represent, mostly it represents chlorine or bromine. You don't see this often with fluorine, but you can. So we're adding some sort of halogen. Halogens exist as diatomics. Do you guys remember what a diatomic is? There are 7 elements from the periodic table that exist as diatomics. Halogens are several of them. Okay, so it's going to be Br2 or Cl2 right here. So each chlorine or each bromine in this molecule, the diatomic, gets added to one of the carbons in the double bond. Now, it doesn't matter which one goes where because they're identical. It's the same. You're adding chlorine atom to both of these carbons. In a minute, we're going to see what happens with water. We're gonna add water to these double bonds, and it will matter. Okay, so just thinking about these, let's do a practice problem. Oh, by the way, one thing I want to mention: you do have to have a catalyst. The catalyst is often some sort of transition metal. Okay, like palladium. So you'll see this on the next slide a lot. Palladium is often, if you're wondering what is PD for, it's the catalyst. What is a catalyst? Do y'all know? At least in general, what a catalyst does.
It's what causes the reaction.
It makes it go fast, okay? It brings the reactants together. We're going to talk a whole lot about catalysts when we get to enzymes. But so if you see PD a whole lot in here, that's what that's the catalyst. All right, so we're going to draw the products that we would get from the following hydrogenation or halogenation reactions. And we're just going to do A, B, and C, and D on the left side. So I'll let you guys do the stuff on the right side for practice problems on your own. Okay, so let's draw these out. So we should get, what do y'all think? I'm going to draw, I know this part of the molecule is going to be the same, but now this is going to be a single bond. Is what I just drew okay? Do I need to add anything else? If I'm just doing the line structure? Because on the line structure, we don't draw in the hydrogens, right? So you can literally leave it like this, and that's acceptable. If it really helps you, you can draw in the hydrogens. Although there are technically 3 hydrogens branched off this carbon. Okay, but I would just leave it simplified how I had it before. Okay, but these would be the 2 you added. All right, cis-2-butene, and we're going to add hydrogen. So what is cis-2-butene? I'm going to zoom in a whole lot so I can draw this. No, I don't want that.
I have a quick question. Sorry, another one.
That's okay, Abby. What's up?
For A on the exam, like if we draw in the hydrogens, is that going to be wrong?
No, as long as you like draw the correct structure. But I mean, again, if you want to check yourself, you can draw them in. But the more simplified you can leave it, for me, the better.
Okay, gotcha. Okay, thank you.
Yeah. Okay, cis-2-butene. Okay, so butene, the parent word here means we got a 4-carbon compound. And cis, that gives us some information. So I'm going to have some methyl groups both pointing up or down. And the 2 tells me where the double bond is. So I'm going to go ahead and draw my double bond. And if it's cis, then I'm going to have a methyl group pointing up, or they're both pointing down. I'm going to have my hydrogens pointing down. Okay. Now these lines, so if you were drawing it in a line structure, you would literally just draw this. okay? Or you could invert it and have those extended lines both pointing down. So that is cis-2-butene. So now if we're adding hydrogen across that double bond, what's our product going to be? Well, it's just that the double bond goes away. Very simple. So now it just looks like this.
What was the second thing you drew?
Do what?
What was the second thing you drew?
This right here, the line structure. It's just the simplified version of what I drew right up here. This is a methyl group up here, Maggie. Okay, this is also a methyl group. So I just, in the line structure, you just simplify all this. Okay, any dead end, we know there's a carbon. So there's a methyl group here, a carbon here, 3 hydrogens, carbon here, 3 hydrogens. And then these joints right here, these are these carbons right here. And there's the double bond in the middle, okay? So if I'm gonna be adding hydrogens across this, so, but now when you have an alkane, it really doesn't make sense to draw it cis or trans anymore. You could just, these are equal. These are the same thing. Does that make sense? You only have cis-trans isomerization when you have a double bond in your molecule. Okay, so that's B. C is going to be trans 3-heptene. So we're probably getting close on time. After this slide, we'll take a break, and then we'll pick up. Okay, let's draw trans 3-heptene. I'm going to come down here at the bottom. So I'm going to draw C right down here, just to have more space. Trans 3-heptene. Okay, so hep. How many carbons are in my structure here? 7. And the 3 means that the double bond, I notice there's one double bond here because the E-N-E ending. The 3 means that the double bond occurs between carbons 3 and 4. Okay? So I'm going to, it's a trans, so I'm going to draw carbon 1 to carbon 2, carbon 2 to carbon 3, carbon 3 to carbon 4, and boom, there's my double bond. Carbon 4 to carbon 5, carbon 5 to carbon 6, and carbon 6 to carbon 7. Now, what's nice when you draw it in a zigzag line like this, it's already trans. There would be, so this is the carbon substituent branching, you could say up, or yeah, up, and then you would have the little hydrogen branching down, because there is a hydrogen branching off this carbon. And then you have this other carbon substituent branching down, hydrogen branching up. You see how it's already written trans? You don't have to draw the hydrogens in. I'm just helping you see how this is trans. You got one carbon substituent pointing up and one pointing down. So the carbon substituents are pointing opposite directions, which is the opposite of what we see with cis up here, where they're both pointing the same direction. Okay, so that's trans 3-heptene. Now we're going to add hydrogen across this. So the product that we're going to get when we add hydrogen, what's going to happen? The double bond's just going to go away, right? So this is actually really simple. All we draw is a zigzag line. And you thought organic chemistry was hard. You're just drawing zigzag lines. One time I met somebody who had a cat, and their cat's name was Zigzag. And I was like, how did you arrive at that? It's funny, I'll ask my daughter a lot of times now, like, you know, we read Disney books and all kinds of stories that have dogs and animals. And so she always talks about if she has an animal, what she's going to name it. But she hasn't told me Zigzag yet. Okay, that's it. Do you guys see how this, any questions on C? The double bond just goes away. Is this confusing to anybody?
So the hydrogens that were added would go.
Yeah, so we still have this hydrogen here originally that we had.
Okay.
And we still have that hydrogen here that's original. But now we have two. We also have another hydrogen. I'm going to just branch it back off that carbon. Okay. And then this carbon would also now have, these are the new hydrogens.
Perfect. Okay, awesome. Thank you.
Yep. And
Will
you
the
see,
product, I'm sorry,
go ahead, Madison.
will the product of an addition always be saturated?
Let's go back and check.
So it'll never have a double bond?
Yields a saturated alkane.
Okay.
Now, when we get to fatty acids, sometimes really long chains of hydrocarbons, such as fatty acids, like literally they can look like this. You know, you just feel like you keep going for miles and miles and miles and miles and miles. And sometimes fatty acids have like multiple double bonds, okay? And sometimes when they actually do hydrogenation, like commercially or industrially, sometimes you don't actually desaturate all the double bonds. Sometimes it is imperfect, okay? But for now, for simple ones like this, where I'm just giving you a compound that has one double bond, yes, it yields a saturated compound, okay? Yes,
Thank
it's
you.
saturated compound. Okay, let's look at D, and then we're going to take a break because we're at time. We got this ring structure. This is a pentene ring because it's 5-carbon ring, and there's one double bond. And we're adding hydrogen across it. So literally all you draw is the same thing, but without the double bond. Okay. So the double bond goes away. The hydrogens are added, but we don't draw hydrogens in a line structure. So you just draw it like this. Okay, now if you wanted to see it, where did those hydrogens go? One is branched off this carbon. That's the new hydrogen. And one is branched off that carbon. That's the new hydrogen. Okay. But in the line structure, I'm not going to draw those in, and you don't have to draw those in.
So in the end product, regardless, you're just taking away the double bonds.
Just taking away the double bond, Maggie. Yep. Now, when you're adding halogens, okay, you do have to write the atoms in. So I'm going to do one real quick. I'm just going to show you like D here. When we're adding halogens like bromine, you do have to write the bromine atoms in. Okay, so now bromine would be added one to this carbon and one to this carbon. So when you guys go practice all these over here, the double bond goes away, but you do have to draw these in on a line structure. Okay, the halogens. All right, we're gonna take a break. I need some coffee. I'm learning a lot today. I'm learning that I really don't like it when my iPad doesn't work. I feel like, oh man, this has been challenging for me, guys. So thank you so much for your patience. I probably don't explain things near as well when I'm flustered either. So sorry if today's not been super clear, but we got probably 10 more slides to hit when we come back. So we're going to get over those and then we'll do the lab, and we should have plenty of time to do that lab. Okay.
What time do we
Take
need to come
care.
back?
Let's say 10:50. Let's get a 20-minute break in. I need to go get some coffee. All right, 10:50. I'll see you back. Bye.